And now for the moment we've all been waiting for. It's all leading up to this. Nerds.
On the 18th of November, 2014, the user at IP address 199.27.133.122 asked, why doesn't someone just solder a bunch of resistors together and use a laser to measure their resistance?
Hey, this is Steve. Welcome to episode 1 of Nerd Snipe. Today we're going to be looking at the infinite resistor grid problem that was shown in the origin story. You might have also seen this on XKCD or in electrical engineering school or potentially on a Google interview, but it's not exactly something that everybody's going to be interested in, which is fine, but it is the namesake problem for this channel. So today we're going to be looking into the solution. Alright, so the first thing that we need to understand in order to be able to solve this problem is what is a resistor and how does it work. Usually people relate it to water flow. So if you have a very small pipe, you're not going to fit very much water through, but if you have a very large pipe, you're going to be able to fit a lot of water through. And so resistors are just these little pieces, little components that you might have seen in a circuit before, and they just resist the flow of electricity.
So here's the symbol for a resistor. You can write it out as 1 ohm. I'm actually going to be using 1 kilo ohm, so there's going to be a little bit of a difference, but the math's going to work out to be the same. So you can either hook up resistors in series, in which case you just tie them end to end and add them together to get the new resistance, or you add them up in parallel where you're basically giving the resistor an option which way it wants to go through the circuit, which lowers the resistance. This is the inverses. Now the easiest way to get our problem is just to add 3 resistors in parallel. That will get us from point A to point B. It's 3 1 ohm resistors, which is 3 ohms. Now if you want, you can add another series of 3 resistors in parallel with that original, which is going to cut the effective resistance in half. But what happens when you add in just this one last resistor here? Well, you can look at it 2 ways. Is it that these ones are in series now, or is it kind of more like, hey, these ones over here are actually parallel with each other? This adds a whole new layer of confusion, and we're going to have to learn some more math before we can understand this. So the first thing you need to know is Ohm's law, which is the voltage is the current times the resistance. You also need to know Kirchhoff's voltage law, which is the sum of voltages around any closed loop equals 0, and Kirchhoff's current law, which is the current flowing into a node equals the current flowing out of a node. So now we actually have everything we need to know to be able to solve this circuit.
Alright, so let's break this circuit down now using Kirchhoff's laws. Because of Kirchhoff's current law, we know that the amount of current that's going to flow into this node is also going to be equal to the current that's going to flow out of this node. So we know I naught equals I1 plus I2 plus 1 I2, and that has to equal 0. That's Kirchhoff's voltage law. So have you ever been on the internet and you run across one of these where somebody shows you a grid and it says, how many boxes do you see in this grid? Well, if it's a simple grid where every box is the same size and it's a perfect square, we can solve that one pretty simply. So what we're going to do is we're going to take and say, okay, well if it's a 1 by 1, we have 1 box. Pretty straightforward. Now if we bring that up to 2 by 2, well now we've got the big box plus the 4 little boxes. So that's going to be a total of 5. Make that 1 bigger to 3 by 3 cube, or 3 by 3 square. Now we've got the 1 big box, 1, 2, 3, 4 little boxes, plus the 1, 2, 3, 4, 5, 6, 7, 8, 9 other boxes. The equation on this one, well that's going to be this. You have n squared, however many you have on your length and width, it has to be a square for this, plus
n minus 1 squared. Alright, so R equals 7 over 5. So that's going to be 1.4, and we'll see if we got our math right. 1.394. The math has worked. So now that we've finished 2 pages of math, I'd like to thank our sponsor. Keysight Technologies is what I'd like to say, but I don't have a sponsor. You can at least understand and appreciate after 2 pages of math why this problem gets immensely difficult. We were just trying to solve this with 2 loops. That's all. And not an infinite grid, just 2 loops. And it ended up taking 2 pages of math with 8 different equations, 6 different variables. So obviously, doing it using traditional means is not going to be feasible. But today, what we're going to do is we're going to build it. So if you recall, when I started building the circuit, 3 resistors in series gave us 3 k ohms. When we added 3 more in parallel, it gave us 1.5 k ohms. Adding in that extra resistor dropped us down to 1.4 k. So as I start building this circuit, pay attention to how much the diminishing returns are for every resistor or every box that I add to the lattice. I should count how many times I've burned myself. That's 2. I think I soldered more for this than I have for everything else in my whole life. It's 3 burns, but I knew that one was coming. And so that's actually pretty interesting. We've now got our 2x2 grid here, and the resistance is actually dropped by quite a bit just by adding this path that goes out the wrong direction and back up in. We've actually dropped the resistance by almost 200 ohms, so it's down to 1.203. We're below 1K already, just with this many. I mean, really, that's not that impressive. We could have gotten below that with just, 1 resistor. But now that we got this many, I had to figure out the math on how many resistors I was using. So starting off, just to get a box of a 1x1, you need 4 resistors, 1 for each side. But then if you're going to add another box to make it a 2x1, you only need to add 3 resistors. This is going to be true anytime you try to add a row or a column, that you're going to need 3 resistors. But once you have those rows and columns already established, you only need to add 2 resistors. So how many resistors have I used right now as a 3x3? Well, the equation that I found for that is 2 times the number of rows times the number of columns plus the number of rows plus the number of columns. So for a 3x3, we're looking at 24 resistors. I also found out with the 600 resistors I bought, I can make a lattice that's 16 by 17. So here we are. I got the 8x8 lattice laid out now. That's 64 boxes, and diminishing returns are really starting to kick in now. I think last time we measured we were at 814. Now we're only at 806, and so we're approaching that limit as it goes towards infinity. So we're going to have to do a lot more resistors now to get any progress. 9x9, 798. 10x10, 794. 11 by 11, 791. 12 by 12, we're sitting at 787 now. 13 by 13, 784. So growing up, hearing the phrase, the whole 9 yards, I think of football. And the whole 9 yards doesn't get you anywhere in football because you need 10 yards to get the first down. So that term never really made sense to me until one day I looked it up, and the best theory of what giving the whole 9 yards is in World War II, the munition for the machine guns was supposedly in 9-yard increments. And so when you're giving it your all, you gave it all the ammunition you had, you gave it the whole 9 yards. 15 by 15, 782. Only one more row to go.
And now the moment we've all been waiting for.
The real mathematical solution. But unless you're really comfortable using Taylor series, Fourier series, eigenvalues, and basically all deep levels of math, it's not going to make a whole lot of sense. So we're just going to dig down and look at the solution. The solution we're interested in is 4 over pi minus 1/2, which works out to be about 0.774.
So even though they did the math to solve it, one of the problems is, as you go towards infinity, things really start to break down because, well, you can't go to infinity. As the current tries to go out towards infinity and it runs into more and more resistors, well, the resistance goes to infinity as well. So which one of those things is going to trump? The other problem is you can never actually get towards infinity, so the infinite equation that gets solved isn't even valid itself because the current, a real physical thing, can only move as fast as light speed, and it will never get to infinity. And now the moment we've all been waiting for, it's all leading up to this. 611? That's way less. Just kidding. Pull that off right there. 781. So it's a little bit more than what the mathematical value computed. I think that was 774, so we're sitting at 7 ohms above. But all things considered, that was something I couldn't have done. This is something that I could do. And we got pretty close to the right here. So I can't believe how many people already watched the origin story. And this one's going to be very deep for most of you. But thanks for watching, and you just got Nerd Sniped. Do we have a bad resistor? Oh man. Well, it's going to screw some stuff up. What am I going to do with this now?